An ordinary annuity is a sequence of equal payments made at the end of equal periods of time. So what happens with an ordinary annuity is an account is opened with a certain interest rate, and at the end of, say, each year, for a chosen payment period, it could be a month, it could be semi-annually, but at the end of each year, a certain amount is deposited. So let's say we deposit $1,000 at the end of each year, and we have the account open for 5 years. Well, the most recent deposit of $1,000 wouldn't earn any interest. But the deposit before that, from the year before, would earn 1 year of interest, and the deposit before that would earn 2 years worth of interest, so that's like multiplying by the rate 2 times. The year before that would earn 3 years worth of interest, and then the initial payment at the end of the first year would earn 4 years worth. So what this ends up looking like is the geometric series, the finite geometric series, which is how we arrive at the equation f equals p times the quantity 1 plus I to the n minus 1 over I. So I know that looks a little bit different from this formula, but if you think about it, the x is the 1 plus I, so in my example that was 1.08, and then we subtract 1 from both, and we multiply by the payment at the end. So P stands for the payment. So in this formula, F is the future value, P is the payment at the end of each period, R is the annual interest rate, M is the number of periods per year, and I is the interest rate per period, which we calculate as R divided by M. Then N is the total number of periods. So the reason that geometric sum works is that the money that's in the account at the beginning gains more interest than the more recent money put in the account. So the longer those deposits are in the account, the more money they earn, the more interest they earn. So this first deposit earns more interest than the final deposit. Let's do an example. Example 1, find the future value of an ordinary annuity with payments of $500 and interest rate of 1.5% compounded semi-annually for 8 years. So first, let's find all of the components we need. P, the payment, is $500. The rate R is 1.5%, changed to a decimal is 0.015. And the number of compounding periods per year is semi-annually, so that's twice per year, so M is 2, which means that the rate per period, I, which is R over M, is equal to 0.015 over 2. Which is 0.0075. And then last we need N, the number of compounding periods, total, which is the number of years, which is 8 years, multiplied by the periods per year, which since it's semi-annually again is 2. So 8 times 2 gives N equals 16. Then we have the information to set up this formula. So we get F equals P, which is 500, and that means that 500 is deposited semi-annually, so twice per year, multiplied by the quantity, one plus I, which is 0.0075, minus 1, over I, and then the quantity in the parentheses, 1 plus I, we raise to the n power, so to the 16th power. And then we calculate this in one step, being careful not to round until the very end. So calculating that, we get that the future value is $8,466.14. Example 2, you deposit $6,000 in an account with 2% interest compounded annually at the end of each year for 10 years. What is the value of the account after 10 years? So using this equation, we need the payment amount, which is $6,000 at the end of each year. We also need I, which we get using the rate. So the rate is 2% or 0.02. And then the number of periods per year, since it's compounded annually, that value M is 1, which means that the interest rate per period is just the rate, because it would be 0.02 divided by 1, so it's just 0.02. And then the total number of compounding periods, N, is equal to the number of years multiplied by the periods per year, so just 1 period per year, so 10 times 1, and there are 10 compounding periods. And now we have the information to set up the equation. So F equals the payment of $6,000 multiplied by 1 plus I, which is 0.02, to the N, which is 10, minus 1 over I, so 0.02. And then after setting up the equation, we use a calculator to find the future value. $65,698.33. That is the future value. Our final example will involve a sinking fund. Now, a sinking fund is a fund that a business sets up to pay off amounts, and if payments are equal at the end of periods of regular length, then the sinking fund is just an ordinary annuity. So, for the purpose of this example, we'll use the same equation as for ordinary annuities. So example 3, a business sets up a sinking fund by depositing $10,000 into the fund at the end of each quarter. The account earns 5% interest compounded quarterly. How much will be in the sinking fund after 10 years? So the payment amount is $10,000. And the rate is 5% as a decimal, 0.05. The compounding periods per year is 4 because this is quarterly compounded interest, which means that I, the interest rate per period, is 0.05 divided by 4. So I is 0.0125. And then last N is the total number of compounding periods, which is the number of years, which is 10, multiplied by the periods per year, which is 4. So N is equal to 40. And now we have the information to set up that equation. So F equals P, which is 10,000, multiplied by 1 plus I, to the N, minus 1 over I. And then we calculate, being careful not to round until the last step. So the future value is approximately $514,895.57.